section 5.5, exploiting block structure for determinants. So this is similar to what happens with block matrices in matrix multiplications and inverses. Calculating determinants can be also simplified for block matrices. And this is not just for making calculations on paper easier. For large matrices, even with computers, the calculation might become too much, and too many unnecessary work can introduce too many rounding errors. So reducing the complexity of calculations is very important in practice. Lemma 5.17 about the determinant of block triangular matrices. If A is an n by n complex matrix and it's block triangular matrix, which means it's either upper block triangle or lower block triangle with A11, A12, 0, A22 structure, or A11, 0, A21, A22 structure. And the blocks are square blocks. A11 is P by P, A22 is Q by Q. And of course then the A12 is not necessarily square, but the diagonal blocks must be square. Then what we have is that the determinant of the whole matrix A can be calculated as the determinant of A11 block times the determinant of the A22 block. And probably the easiest is to use Jordan form, J1 and J2 for A11 and A22. So that means that A11 is U1, J1, U1 inverse, and A22 is U2, J2, U2 inverse. And we only consider the upper triangular case. The lower triangular case is done the same way. So what we can do is write this A11, A12, 0, A22 structure as for A11 we substitute the U1, J1, U1 inverse. Similarly, we substitute the Jordan form for A22. And then a big step is that we notice that the diagonal matrix U11, U22, its block diagonal, can be factored out on the left, and on the right, the U1 inverse, U2 inverse block diagonal matrix can be factored out. Well, we have to be careful with this. We have to check what happens with the A12. So this part gets multiplied with U1 from the left and with U2 inverse from the right. So in order to not to have extra parts there, we have to add the U1 inverse on the left and U2 on the right, so that those things cancel out and you really get back just A12. So this part is easier actually to check going backward from this line to the previous line. Then once we have this, you can also notice that the way we invert block diagonal matrix is that we just invert the block diagonals. That means that the U1 inverse, U2 inverse matrix is the same as U1, U2 inverse. And then we have this similarity transformation that V an upper triangular and V inverse. So notice that this is not just block upper triangular, but J1 and J2 are actual upper triangular matrices in the middle. And what we have is that in the diagonals we have the eigenvalues, of course, for J1 and J2 in the middle of this multiplication. And we also have that the determinant can be calculated factor by factor. So this is the same as the determinant of V from the left, from the right the determinant of V inverse, and the middle we have the determinant of this middle part, which is again upper triangular. There is nothing in the lower triangular part, and it's not just block upper triangular, it's regular upper triangular, which means that the determinant is just the product of the diagonal entries that are actually in the upper triangular J1, J2 matrices. So that means that it's just the determinant of J1 and multiply with the determinant of J2, because those are also just the product of the diagonal entries. And then, of course, we can write this back in the form of U1, J1, U1 inverse, because that's coming from a Jordan form. And again, we have, for the determinant, we have this rule that we can calculate the determinant factor by factor. And also here we use that the determinant of the inverse is the reciprocal of the determinant of the original matrix. So these cancel out. And similarly, the U1 inverse determinants cancel out. Same thing for the J2 matrix. We can replace it with the determinant of U2, J2, U2 inverse. And the reason why we want to do this, because these are the A11, A22 matrices. So comparing the beginning with the end, we have what we wanted, that the determinant of A is the determinant of the diagonal blocks multiplied together. There's an alternative proof that can be done using the factorization EPA equals U from the Gaussian elimination. We also did similar proofs before where we exploited this structure. But I'm pretty sure that this is easier this way. Blocks can be used not just for block triangular matrices, but actual block matrices. So here's an example to calculate the determinant of this matrix. It's how many rows, how many columns, 2, 4, 6, 7 by 7. And the point is actually to do it by hand right now. So we can observe that if you split this up into blocks, this is actually a lower block triangular matrix. So this is a diagonal block, this is a diagonal block, the red and the blue, and then we have a lower block. So according to this previous lemma, the determinant equals to the determinants product in the determinants of the block diagonals product. And the nice thing is that the first one, this is a upper triangular, which means its determinant is the product of the diagonal entries 1, 2, 3, 4 multiplied together. Now for this one, we might want to expand it using the first column. Starting with 1, we get 4 times 2, the 4, 1, 2, 2 determinant. And this is 4 times 2 minus 1 times 2. So we end up with 24 times 6, which is 144 as a determinant. And the idea is that we don't have to calculate much because we observe some shortcuts here. Theorem 5.19, if A is a n by n complex matrix that can be expressed in block form, A11, A12, A21, A22, we don't assume anything about upper or lower block triangular. The A11, so the diagonals should be block. That should be A22. Clearly, if A11 is k by k, then A22 will be n minus k times n minus k on the diagonal. So the theorem says that if A22 is invertible, then the determinant of A is the determinant of A11 minus A12, A22 inverse A21 times the determinant of A22. And if A11 is invertible, then the determinant of A is determinant of A22 minus A21, A11 inverse A12 times the determinant of A11. Now from these multiplications, you might guess already that this is coming from the Schur complement of A22 and A11. We have two different Schur decomposition. And this was called, the one is the Schur complement of A22 with respect to A. So A can be decomposed into an upper triangular, or actually two upper triangular, block upper triangular, and block lower triangular. In fact, the first one is regular upper triangular, since it has a diagonal ones in the diagonal entries and then some stuff above it. And also the last one is lower triangular. And actually the middle one is block diagonal. So once we decompose A this way, we calculate the determinants factor by factor, and then we can use the previous lemma because we have upper and lower triangular matrices, and we have let's see, what do we have here. So we have actually regular upper triangular with ones in the determinants. That means its determinant is ones in the diagonals. So that means the determinant is 1. Also the last matrix gives you determinant 1 because it's lower triangular with ones in the diagonal. And the middle one, because it's block, we get using the previous lemma, really it only applies to the middle one, that this is the determinant of the diagonal entries multiplied together, the diagonal blocks. And the second part is really very similar, it's just different decomposition with lower triangular, upper triangular matrices again. Section 5.6, the Binet-Cauchy formula. I believe these are both French. Well, Cauchy was a French-German mathematician, but the way we pronounce the names are Binet, with silent T at the end, and Cauchy. So this is about the determinant of a product, which can be expansive computationally. If you have A matrix, which is a k by n, and the B matrix, which is n by k, then already to calculate the product AB has a complexity of k times n squared, although it can be improved a little bit, but the natural way to calculate it, especially on paper, is using this straightforward calculation that ends up with k times n squared of order of calculations. So the idea is that for n greater than or equal to k, we can use square blocks of A and B to calculate the determinant of A times B. Also notice that the product rule for the determinant doesn't apply here because A and B are not necessarily square. So it wouldn't make sense to calculate the determinant of A or the determinant of B. These are rectangular matrices multiplied together, but the result is square, and for that the determinant makes sense. So we defined this C matrix, which is a P by Q matrix in general, and there is a notation C and then one row I1 through IK and then another row J1 JK. And what this is the determinant of the matrix with entries I1 J1, I1 J2, I1 JK, first row, and then the last row is CIK J1, CIK J2 up to CIK JK. So the I's, the indices in the first row, indicate the rows that we are choosing from the C matrix, and the J's in the second row are the columns that we are choosing. So we have the I1 through IK rows and the J1 through JK rows. Because we have K rows and K columns, this is a K by K matrix, and it's called a K by K sub-block. So for example, if you look at this 7 by 6 matrix, doesn't have to be square matrix, 7 rows and 6 columns. And let's consider C2, 3, 6, 1, 4, 5. So that means we choose the second row, third row, and the sixth row, but not all entries from these rows, only the first column, fourth column, and the fifth column. So we have 2, 1, 2, 4, 2, 5 indices, then 3, 1, 3, 4, 3, 5, and 6, 1, 6, 4, 6, 5. And then you have to look these up, where the 2, 1 is, it's 5, then 2, 4 is 2, and 2, 5 is 0. And similarly, the other entities, for example, 6, 1 is 1, 6, 4 is 3, and 6, 5 is 4. Then, if we're using this notation, we have the so-called Binet-Cauchy formula. If A is a k by n matrix and B is a n by k matrix, and k is less than or equal to n, then the determinant of A times B is the sum as the j's are going through from 1 through n, and all of them should be less than the next one. So J1 is greater than or equal to 1, less than J2, less than J3, and so on, less than Jk, less than or equal to n. So we have k columns. And from A, we use the first k rows, and then all the possible k columns in increasing order. While from B, we choose these columns, J1 through Jk columns. These are the rows. We choose the J1, Jk rows. That's the upper row. And the columns are the first k columns. In fact, A is supposed to have only k rows and B is supposed to have k columns. So what we are doing is we are just choosing all the rows of A, and then the different possibilities for the k columns from all the columns. And similarly, we choose all the columns of k or of B, and we choose just k different rows from B. Here is an example. A is a 2 by 3, B is a 3 by 2. The result is supposed to be a 2 by 2 matrix, and then it's supposed to have a determinant. So we have that k equals to 2 is less than n. The requirement is less than or equal to n, where n is 3. We have to choose 2 columns from 3 in increasing order. So it's n choose k in this case, 3 choose 2. You can do it 3 different ways. So that means that we have 3 different products added together. From A, we have, well, the first 2 rows always, because only we have 2 rows. And then we start with 1, 2 column. Then similarly from B, we have the 1, 2 rows and the 1, 2 columns. Then still for A, we always use the first 2 rows, 1, 2, because that's all we have. And also the last term, actually, we're going to use the first 2 rows. But the thing is that how we choose the columns. So we have to choose 2 columns. We can choose the first and the second, or the first and the third, or the second and the third. So we have increasing order of the columns, and that's all the possibilities there. Then once you choose for A, then B is automatic because it has all the 2 columns, and then it has the same choice of rows as the choice of columns in A. So if it was 1, 2 here, this is 1, 2. If it was 1, 3 here, then it's 1, 3. If it's 2, 3, then it's 2, 3. So first 2 rows, first 2 columns, that's 4 minus 5, 5, 3. Then the same thing about matrix B, first 2 rows, first 2 columns, 8 minus 4, minus 1, 1. Next, first 2 rows and 1, 3 columns, so 4, 5, 3 minus 7, and 1, 3 row, minus 8, minus 4, 9, minus 6. And then finally, columns 2, 3, so minus 5, 3, 3 minus 7 from A, times the determinant of B taken out the first two, the second and the third rows. So minus 1, 1, 9, minus 6. And these are already 2 by 2 determinants, so we can calculate them by hand. 12 minus minus 25 plus 25 minus 8 times minus minus 4 minus 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 4. Then 4 by minus 7 minus 28 minus 3 times 5, 15 times 6 by 8, 48 minus minus 36 plus 36, and finally 35 minus 9 and 6 minus 9. So that's altogether, if you calculate it, we end up with a minus 4134. Don't forget to check your answer with MATLAB. In MATLAB, the command is just det. Section 5.7, minors. So we turn our attention to minors, which is the traditional way to introduce determinants in undergraduate courses, actually. So you might know already about them. But again, we will use them not just for calculating small determinants, but also for theoretical purposes. So the definition is that the ig minor, denoted by A sub ij, of a matrix n by n matrix, which is complex maybe, is defined as the determinant of the n minus 1 by n minus 1 matrix that is obtained by deleting the ith row and the jth column of A. For example, if you have this A matrix here, then the A11 minor is, you delete the row of 4 and the column of 4, so we end up with 3 minus 7, 1, 0. Then, for example, the minor A13, first row, third column, that's 3, so you delete this row and this column, and you are left with 5, 3, 2, 1. And, for example, the 3, 2 minor, third row, second column, so we delete this column and this row, you end up with 4, 5, 3 minus 7, and so on. So these are just examples. Altogether we have 9 entries, and you can choose any of the 9. Theorem 5.24. If A is an n by n matrix, then the determinant of A can be expressed as an expansion along the ith row. So that means we don't just have to use the first row. In fact, I already used the first column here to expand one of the determinants, not paying attention how we defined before. So for small matrices, it is used actually in these ways, the calculation. So the idea is that we can use any row or any column. You can use the ith row or the jth column to expand the determinant. And the way it goes is that in this first case, when you use the ith row, so we sum up in the row, the ith row, we have aij entries as the column index j goes from 1 through n. And then for each of the ij entries, we consider the ij minor, and that's a determinant that we multiply the ij entry with. And then we also have an alternating sign, minus 1 to the I plus j. And alternatively, we can also use the jth column. So the determinant of A can be also calculated using the sum of aij as I goes from 1 through n. So we go through the jth column with the row index I changing. And again, each of these entries is multiplied with the minor aij times the plus minus sign from minus I to the I plus j. So the idea is, the way we can use this is that if you have a row or column with many zeros, the most zeros, then it's good to use that row or column. Because in the other cases, when A is 0, then you don't have to calculate the minor. Since it's multiplied with 0, it will be 0 anyway. The powers -1 to the I plus j create an alternating sign pattern. This is in addition to whatever sign the matrix entries have. So Aij might be positive or negative, the determinant ij can be positive or negative, whatever they come out to be, and then this additional ±1 might change the sign. So the way it looks is that if you start from the upper left corner, that's positive, and then moving right or below, you get negative, positive, negative, negative, positive, negative. And then you have alternating sign in each direction. And also, I already mentioned before, let me mention again, the MATLAB command to calculate the determinant is det parenthesis A. Example 5.26, calculate the determinant by expanding in minors along the column or row with the most zeros for the matrix A. This is a 4x4 matrix. So look at the rows, we have 1, 2 zeros, 1, 2 zeros. Look at the columns, 1, 0, 2, 0, 1, 0, 3 zeros. So the last column has the most zeros, 3 zeros. So we use this column. The formula is that for this column, the row index I goes from 1 through n, and the column index is 4. And then we have to calculate the corresponding minors, ai4, and multiply it with -1 I plus 4 power. So starting with I equals 1, this is a14 minor a14 times -1 to the 1 plus 4, and then a24 -1 to the 2 plus 4, a34 times a34 -1 to the 3 plus 4, and a44 -1 to the 4 plus 4. Because the entries in the fourth column are zeros except the 4 entry, what we have here is 0, another 0, another 0, and from a44 we have 2. Then we have the determinant of the submatrix that you get if you cancel the fourth row and the first column, the rows and columns of this entry A44. So then we end up with this submatrix, which is 3 by 3. Now the first and second columns and the second and third rows all have 1, 0 in them. So in that sense, it doesn't matter which one we choose. Let's choose the first column now to continue by expanding in minors this. Notice the additional negative sign due to the alternating sign. So here previously we had -1 to the A, which is positive. Now, so we still have this 2, and then the determinant of the 3 by 3 matrix. Let's choose, what are we doing? We are choosing the first column, so we have -5, and then cover the first row and first column to get this 4 -4 -4 3 matrix if we delete the row and the column of -5. Then we have expanding it along the first column, so we start with negative sign. We start with positive alternating sign, and then the next one is negative. So that means that we have additional negative sign, and then we have -2 because it's what entry is there. And then what we get if you cover the second row and the first column, the row and columns of 2, then we get -1, -4, 4, -3 for this determinant. And then of course we can calculate the 2 by 2 determinants. So we end up with, after some calculation, with 84. All right, so I'm not saying that this is easier, at least not for 4x4 matrices. It might be better some other way. But this is an important theoretical application of the determinants. So the next theorem is that for a n by n matrix, we defined C n by n matrix with entries that are theCij's minus 1 to the I plus j times the minor Aij, or Aji. Sorry, actually this is important here. Let me try to highlight it. And this is kind of tricky, that for the Ij entry of this C matrix, we will use the Ji minor. That means that the thing that you get by removing the jth row and the ith column. So if we define this matrix like this, then we have that AC equals CA, and that equals to the determinant of A times the identity matrix. And we also have that if the determinant of A is not 0, then A is invertible, and the A inverse is 1 over the determinant of A times the C matrix. So the proof of this, we expand the following matrix using the ith row. We have let's have the determinant of this, looks like the A matrix with entries A11, A1n, AN1, ANN, except the ith row is replaced with x1, x2, x3, xn. All right, so then we can also write this out as, I think I made a mistake here. So if this is the ith row, then this is the I1 entry. So that means that we need 1i minor, and similarly for x2, which is in the I2 entry, we need 2i minor, and so on. We have the 3i minor, and finally the n1, or I'm sorry, ni minor. Instead of the in, and for the in entry, you get the ni minor. And we also have alternating signs. So starting with 1, here we have I plus 1 for the plus minus sign for the power of minus 1. And then we just add 1 and 1 and 1, so we get I plus 2, I plus 3, and so on for the powers of minus 1. And then let's look at this, what we have here. If you look at this, these pairs of products, and the indices are again mixed up. Yeah, so it is a little bit strange. But this is what it is. 1i, 2i, 3i, and then ni. Like a column vector with also signs minus 1 to the I plus 1, minus 1 to the I plus 2, and so on, up to minus 1 to the I plus n. And then the row vector in front of this x1, x2, xn. Yeah, so if you do this row vector times column vector multiplication, or 1 by n multiplied by n by 1, you get exactly this sum. And then notice that if these x1, x2, x3 are actually I1, AI1, AI2, AI3, that's the actual ith row, then this formula gives us the determinant of A. On the other hand, if x1, x2, x3 vector equals to any other row, then according to the properties of determinants, which is more precisely it was a lemma and the part 1 of the lemma. So if you have any other row for this x1, x2, x3, that means the ith row is replaced with another row, and we have a duplication of rows in this case, and that means that we get a 0 determinant. So this thing can be summarized in the following. For the ith entry, we get, if we have the ith row, multiply with this, we get 1. And if you choose any other row, you get 0. So this is also multiplied with the determinant of A. So we have the determinant of A here, but we can factor it out. If you check what the definition of the C matrix is, we have this formula, and this is exactly what we have here. This is the first column, and then you would have the second and the third and the nth column. So what we have here is exactly A times C equals the determinant of A times the identity matrix. And then similarly, using the columns of A, we get that C times A is also the determinant of A times I. The second part actually really comes from the first part. So this shows that the A matrix is invertible. And then it equals to, if you divide through with the determinant of A, that should be capital E, then we get that A times C over the determinant of A is the identity, and it's the same as if you multiply with 1 over determinant of A, C times A. So that means this is the inverse of A. From a computational point of view, it is a complete nonsense to use this formula to calculate the inverse. Yeah, so you can see it in textbooks, especially undergraduate one. Please note that in practice, if you have to calculate, I don't know, a 10 by 10 matrix or a large one, it doesn't make any sense. Now for small matrices, it doesn't matter. You can use this formula, you can use whatever formula you want. That's not an issue. For large matrices, that's a problem, how you calculate the inverse. Lemma 5.29 says that if A is an n by n matrix, and we define the function f to be the determinant of I plus x times A, so x is a variable now. Notice that the determinant of a matrix is scalar, so you have a scalar valued function f. Then the derivative of f at x equals 0 is the same as the trace of A. We can use the Jordan decomposition for that, like we used many times this before. A equals u inverse ju. Then for f of x, we can plug in for A the u inverse ju part. We can factorize u inverse on the left, u on the right, and then we get that I stays the same because u inverse u is I, the identity matrix. And we can take the determinant factor by factor. And then the determinant of u inverse cancels the determinant of u. So we end up with just the determinant of I plus xj. So we have the eigenvalues in the diagonal multiplied with x. And it's an upper triangular matrix. So the diagonal entries are 1 plus x times lambda j. And the determinant is just the product of all these entries. So here lambda j are not necessarily different. These are all the diagonal entries really with eigenvalues, and perhaps they are repeated. Then we use the product rule for this form of f of x to differentiate. So the product rule is that you differentiate each factor and multiply it with the rest, like the ith, yeah, that's supposed to be the ith entry there, as I goes from 1 to n, and so that's the derivative of the ith factor with respect to x is lambda I, and then times the rest of the factors. That means j going from 1 to n, where j is different from I. So this is the derivative in general with x in it, and then if you substitute x equals 0, we get just 1s here. The product of 1s is 1, so we end up with just the sum of the diagonal entries, which means the sum of the eigenvalues repeated with the algebraic multiplicities. So that means it's alpha 1 lambda 1 plus alpha 2 lambda 2 and so on, alpha k lambda k. And then we had this theorem on the trace saying that this is exactly the trace of the matrix A. So that means that the derivative of f at 0 is the trace of A. Lemma 5.30 is the so-called Cramer's rule. Very popular, sometimes even in high schools they teach this. Again, please remember, if nothing else, just remember that from a computational point of view, this is a complete nonsense for large systems. If A is a n by n complex matrix, and if it's invertible, that means that AX equals B, linear system has a unique solution for this vector x, then it can be solved the following way. The ith component, it's the determinant of this big n by n matrix where the ith column of A is replaced with the right hand side vector B. And it's divided by the determinant of A. And this I goes through from 1 to n. It's a lot of work, of course, to calculate all these determinants. For example, we can compute the inverse of this matrix, a 3 by 3 matrix with the x variable in it. Of course, it has inverse only in cases where it's invertible. So it's interesting to know when it's invertible for what values of x. So actually the point is that I want to make here that this is not exactly computational linear algebra because of the variable x. We cannot simply use the Gauss-Jordan or Gauss elimination. So then it might make sense now to look at this theoretically and find out for what x there is a inverse. So the formula says that we can calculate the inverse using this reciprocal of the determinant times the C matrix. First of all, of course, the determinant of A shouldn't be 0. So let's calculate the determinant. I use the last row because there are two non-zero entries and the last entry in the last row is 0. So then you have plus minus plus 1, and the determinant, if you cancel the first column and the last row, you get 2, 2, 1, 2, minus x, alternating sign. So if this was plus, then it is minus x times, if you cancel the column and the row of x, you get 1, 2, 2, 2 for the determinant. And then this is 4 minus 2, 2, and then plus, actually minus x times 2 minus 4, so it's minus 2 times minus x is plus 2. So 2 plus 2x shouldn't be 0. That means x shouldn't be negative 1. If x is not negative 1, then the determinant is not 0, which means the inverse exists. Then for these values, we can use the formula that we define this matrix C with the Cij entries minus 1 to the I plus j with the A j I minor. So the C11 is plus 1, and then 1 to x0, which is minus 2x. C12, so C12 we have 1 plus 2, 3 odd power, which gives us a negative sign. And then we need the 2, 1 minor. So the second row, first column, we cancel the row and column, you get 2, 2, x0. And this determinant is 2 times 0, 0 minus 2 times x, another minus, it's plus 2 times x. And so on. It's a lot of small calculations, easy to make mistakes. Try to follow, and especially hard by hand because we need these reversed minors. So the ij entry in the matrix will be the ji minor determinant. So we get all the values, and then the A inverse is just 1 over 2 plus 2x times this matrix. So MATLAB is not really appropriate for that because MATLAB is for explicit matrices with numbers. I haven't tried the symbolic package. There is a symbolic package in MATLAB, but that's not worth trying it since we have Mathematica for free from the university. And Mathematica can do the calculation for symbolic matrices with variables or whatever you put in the entries. It doesn't matter, it just uses the formula. So for example, this command gives you this formula for the inverse. And you can also see from here that of course 2 plus 2x shouldn't be 0. Because the 0 denominator doesn't make sense. Section 5.8, basically this is just a summary of how useful determinants are, at least theoretically. So we can calculate the eigenvalues of a matrix A using this determinant. We can check whether or not a matrix is invertible. We can calculate the inverse of an invertible matrix. And we can even solve equations Ax equals B if A is invertible. In practice, let me mention that calculating the eigenvalues using the determinant means you want to solve determinant of lambda I minus A equals 0, which is a polynomial equation with degree n. And if you have 5 or higher degree, then in algebra there is a Abel-Ruffini theorem that states that there is no formula for solving it in general. We might be able to solve it if we are lucky. You can try to guess. For example, college algebra has a whole section about guessing solution to polynomial equations. In practice, this is complete nonsense because you never have integers in practice, and there is hopeless to guess than a decimal number for a root. So in general, there is no formula. There are always eigenvalues, of course. We have a theorem that says that there are eigenvalues, and you have exactly n eigenvalues, maybe repeated ones. And for polynomial equations, there are n roots, maybe repeated ones, maybe complex ones. But they can be only approximated. And for polynomials, there are no good approximations for the roots. So in fact, what people do many times is if you want to find the roots of polynomials, people convert it into matrices, and then there are nice numerical methods for approximating the eigenvalues of matrices. So again, it's completely useless in practice, only maybe in theory it can be used. About invertibility, we have a similar problem that by the time you calculate the determinant, the Gauss-Seidel method either breaks down, which means that the matrix is non-invertible, or you complete the calculations and you find the inverse. So the Gauss-Seidel method is better than trying to use determinant to calculate the inverse using the Cramer rule. Actually, that's not for the Cramer rule. Solving the equations is the Cramer rule. Again, Gauss elimination is faster and more precise numerically than using the Cramer rule. Section 5.9, companion matrices. So here, actually, we are coming back to this issue that because of the Abel-Ruffini theorem, instead of solving polynomial equations, we rather solve matrix eigenvalue problems. So for example, numerically to approximate roots of polynomial equations is difficult. You might remember using Newton's method. It can jump around, it can diverge, or it can find the root different from what we are looking for. There are many problems with Newton's method. There are some improvements, but still it's not easy. It also requires an initial guess, which can be hopeless in practice again. So it turns out that in approximating eigenvalues can be done, all of them at the same time, and it can be done quite well with so-called iterative methods. This is again numerical methods, numerical analysis. And this has important practical applications also in science and engineering. So let's get to the definition of a companion matrix. A matrix A, n by n, that has this form is called a companion matrix. So look at this, what this is. It's 0 mostly, except the last row is not necessary, 0. Notation is minus A0 minus A1. Of course, depending on what A0, A1 are, it can be positive or negative. And then the diagonal is 0 except the last entry, and this is the upper off diagonal where you have the super diagonal where you have the ones. So this is called a companion matrix. Again, companion matrices play a significant role in the theory of differential equations and also in the theory of so-called Bizosians. And it is discussed in chapters 13 and 21 of the textbook, if you are interested. The big theorem for companion matrices is that if A is an n by n companion matrix with distinct eigenvalues lambda 1, lambda k, having geometric multiplicities gamma 1, gamma k, and algebraic multiplicities alpha 1, alpha k respectively, then the determinant of lambda I minus A is A0 plus A1 lambda plus and so on, adding up to an minus 1 lambda to the n minus 1 plus lambda to the n. So basically coming from the last row. Also, all the gamma j's are 1, the geometric multiplicities. Also A similar to the Jordan matrix J with diagonal entries C lambda 1 alpha 1, C lambda k alpha k. And what this really means is, what this really says is that there is only Jordan cell for each, there is only one Jordan cell for each distinct eigenvalues. So there is no repetition here for lambda 1, lambda k, each of them are different. That means there is one Jordan block, Jordan cell for lambda 1, another from lambda 2. Yep. So remember that sometimes we had several Jordan blocks for the same eigenvalue. But in this case, for companion matrices, only one. And we also have that A is invertible if and only if A0 is not 0. Right, so let's go through the proof. We form this lambda I for the first part, lambda I minus A. So we subtract from, we have the lambdas in the diagonal and we subtract from that this companion matrix. So we have minus ones and we have positive sign for A0, A1, An minus 1. And we use the first column to expand it. So we have lambda here. And then if you remove the first column and the first row, we end up with this submatrix minor lambda minus 1, then 0, and down we have A1, A2, An minus 1. Then a bunch of zeros, and the last one is A0. And starting with plus, then minus, then plus. So this is the nth row, we get minus 1 to the n. Is it? Let's see. So if it was in the second, that would be negative. So then we have a minus 1 here. So there is a sign change. Sorry. And then A0 times the determinant of this matrix, which is this with minus 1s in the diagonal and lambdas in the subdiagonal. And then we continue this process. So we have n minus 2. And notice that this first one has the same structure. So this is also companion matrix, but it's smaller. It's n minus 1 by n minus 1. And what else? Lambda. So lambda gets factored out again. And then we have minus 1 to the n minus 2 a1 now from here, and the determinant of the smaller part. And let's see what this is. So we have, because this is lower triangular, this is, and the n minus 1 by n minus 1, the product of the diagonal entries is minus 1 to the n minus 1. So together with this, it's 1, the coefficient. Then if you multiply this out, you get lambda square and this, and then and so on. So we get more and more entries with, this was supposed to be just lambda. If you multiply through with this lambda, and the determinant of this is minus 1 to the n minus 2. So together this is always positive 1. And so on all the way. So eventually you get exactly this polynomial in lambda, which is what we claim to have in part 1. Second part states that the geometric multiplicities are 1. So how can you look at this? Look at the lambda I minus a, and look at the echelon form of the matrix. Basically look at how many pivots you can have. So if AIs are zeros and lambdas are zeros, then we have lambda I minus a of this form. So all the a's are zeros, all the lambdas are zeros, so only minus 1s are here. Look at this, how many pivots you have. This is actually already in echelon form, upper echelon form, and we have n minus 1 pivots. If lambda is not 0, then what can we do? If lambda is not 0, then this is how lambda I minus a looks, especially if after you eliminate the a's. If a's are not zeros, then still these lambdas in the diagonal entries can be used as pivots to eliminate. Except in this last case, we don't really know whether a n minus 1 is 0 or not, or in the Gauss elimination whether it becomes 0. So we have some entry here, it might be 0 or might not be 0. But this is again in echelon form, upper echelon form. So again, in this case, when lambda is not 0, we have that either we have n minus 1 pivots or we have n pivots if this part is not 0. So if you go back to the theory on the dimension of the range, it says that that's the dimension of the number of pivots. So that's either n minus 1 or n is greater than or equal to n minus 1. It doesn't matter what lambda is. If lambda is 0 or lambda is non-zero. Greater than or equal to n minus 1. That means that the dimension of the null space of lambda I minus a is less than or equal to 1 for all lambda, according to the principle of conservation of dimension, because the sum must be 1. So for eigenvalues, we do have that the dimension of the null space of lambda j I minus a must be greater than or equal to 1. Yeah, at least 1, because it's eigenvalue, and we have a non-zero eigenvector there. And now we also obtain that this is less than or equal to 1. So greater than or equal to 1 for eigenvalues, less than or equal to 1 for all lambdas. That means that the only choice we have is that for eigenvalues we exactly have 1. And this is exactly the gamma j, the geometric multiplicity. So we are done with the second part. The third part, the similarity to this Jordan matrix, that's actually coming out from the Jordan cells being counted according to the gamma j geometric multiplicity. So it follows from this second part. A is invertible if and only if A0 is not 0. So it follows from 1, because in 1 what we obtained is that we obtained the formula for the determinant of lambda I minus a. So when lambda equals 0, this becomes minus a's determinant, which is minus 1 to the n times the determinant of a, since we have this multiplication property of the determinants, and this is exactly a0 according to part 1. And then this last part says that the determinant of a is minus 1 to the n times a0. It's invertible if and only if the determinant of a is not 0, which is if and only if a0 is not 0. So with this we finish this big theorem about the companion matrices, its eigenvalues and their multiplicities, and also how you calculate the determinants. Section 5.10, Circulants and Vandermonde matrices. Used again in engineering. In fact, cryptography, this is also used. If you are interested in applications, you can Google what uses of Circulants and Vandermonde matrices have. So here we start with the definition. First of all, consider P to be an n by n permutation matrix on this form. So it's the sum, j goes from 1 to n minus 1 ej plus 1 transpose plus en e1 transpose. And then in that case, the A matrix, which is n by n matrix defined in this form, that it's a0i plus a1p plus a2p squared and so on, plus an minus 1p to the n minus 1, is called the circulant matrix. So the P permutation matrix that we use is not just arbitrary, it's very special because of this j plus 1 form and n1. It's actually a companion matrix, so if you write this down, what it means, the one, what the permutation matrix, you should go back and check what the definition of the permutation matrix with these E vectors is. It says that the j plus 1 row move to the jth row, and then the first row is moved to the nth row. So this has this form, this matrix. One's in this upper triangular, upper diagonal part, 1 here in the n1 entry, and 0 everywhere else. So when you multiply a matrix, another matrix, the second row moves into the first row, third row moves into the second row, and so on. And here we have a0 is minus 1 as a companion matrix, and a2, an minus 1 is 0. Then in this case, A has this form. That's also interesting to look at if you write out the definition of A. You have a0s in the diagonal, a1s up, an minus 1 down, So the index decreases downward, increases up in these super and sub-diagonals. And then according to the companion theorem, we have that the determinant of lambda I minus p is a0 plus a1 lambda plus all the way up to lambda to the n. In this case, all the a's are zeros except a1 is minus 1. And we have the last term, lambda to the n. Then what we have is that the eigenvalues of p coming from the solution of the minus 1 plus lambda to the n equals 0, you get that it's the nth roots of the unity, nth root of 1, but in complex variables we have actually n of them, written in the form e to the 2 pi I j over n, or you can also write it with the cosine and the sine, and the I is the imaginary unit, and j goes from, well, that's another mistake here, it goes from 0, 1 up to n minus 1. And note that these are n distinct eigenvalues, and these are on the unit circle. Definition: a matrix V, n by n matrix of the form ones in the first entry, then lambda 1, lambda 2, lambda n in the second row, and in the last row lambda 1 to the n minus 1, lambda 2 to the n minus 1, lambda n to the n minus 1 is called a Vandermonde matrix. So what we have here is that the Vandermonde matrix V is invertible if and only if the points lambda 1, lambda n are distinct. And this is really just a consequence of the properties of the determinants. So if you have distinct ones, then all the rows and the columns are different. And if two lambdas are the same, then of course you get the same column, which means that according to the properties of the determinants, you get a zero determinant. And that means that V wouldn't be invertible. Property of the circulant matrices is that they are commutative. If you write down, you have one circulant matrix A with coefficients a0, a1, an minus 1, and another circulant matrix B with coefficients b0, b1, bn minus 1. The p is supposed to be the same. It's a very specific p permutation matrix for circulant matrices. So if you write down what a times b is using this summation, and then using the properties of the permutation matrix that they commute, and then the scalar multiplication ai bj, doesn't matter what order you write, you end up this is the same as b times a. Another kind of lemma or exercise, if you want to call it that way, if p denotes the previous permutation matrix, then the null space of p minus zeta j I equals to the span of vj's, where vj denotes the jth column of the Vandermonde matrix V, and zeta j's are actually these roots of the unity, e to the 2 pi ij over n. And also what we have is then that p equals to the v d v inverse, where d is the diagonal matrix with zeta 1, zeta n. So the solution for this is that we write down what v times d is. Actually, we start with kind of the right-hand side. So V was this Vandermonde matrix. And now we used for lambdas, instead of lambdas, we use the roots of unity. Zeta 1, zeta 2, zeta n. And we have the diagonal entries, the diagonal matrix D. So you have to check what happens when you multiply a diagonal matrix from the left. First row picks up zeta 1, then in the second row you get zeta 1 square, and in the last row we get zeta 1 to the n minus 1 times zeta n, so that's zeta 1 to the n. Then in the second column You get the second column if you multiply the first row with the second column where you have only zeta 2. So that gets picked up, and you get then increasing powers. And then since these are the roots of unity, the nth roots of unity, this last row becomes 1. And if you also calculate p times v, where p is this permutation matrix, and we already have what v is, so this moves the second row to the first, and so on. So it moves all the rows up 1, except the first row moves to the last row. And if you compare the two, you get that p times v equals v times d, which is exactly saying that p equals v times d times v inverse. And then separating this same statement, p times v equals v times d, column by column, we get that p times vj is vj times lambda j. Well, more precisely, in this case, we have the zeta j's for notation of the unit of the nth root of the unit, which is the same as zeta j times vj, since zetas are scalar numbers. Another exercise, if A is an n by n matrix, and it's a circulant matrix with coefficients a0, a1, an minus 1, and if p lambda is the polynomial with these coefficients a0, a1, an minus 1, and increasing powers of lambda, then we have that A equals to v times d times v inverse, where d is the diagonal of p zeta 1, p zeta n, and here again zeta j's are the nth roots of unity. In this case, j goes from 1 to n because we already subtracted 1 from j. And v is the Vandermonde matrix with lambda j equals zeta j in its entries. And also we have that the determinant of A is just the product of the polynomial p evaluated at zeta 1 times all the way to zeta n. So the first step to show this, we have with the columns vj of v, as j goes from 1 to n, we have term by term, we can calculate what A times v means. So we have a0 vj, then that equals to, of course, a0 vj. There is no change there. But then the second term, a1p times vj, we have that the eigenvalues of p are zeta j. So that means that p vj is zeta j vj. That's from the previous exercise. And a1 is just there. And so on. The last term is a n minus 1 p to the n minus 1 multiplied with the vj column vector. So here we get to apply p n minus 1 times, and each time you apply, you get the eigenvalue zeta j once. So you get zeta j to the n minus 1 times vj. Then putting all these together term by term, for a, we get a times vj, term by term multiplication. And on the right hand side, if you add these up with vj on the right hand side factored out, we get exactly p of zj, the polynomial p evaluated at zj. So then putting all these vj together into the v matrix, we get that a times v equals z times v with this v diagonal matrix with p of zj. And we also have that the determinant of A is the determinant of v times z times v inverse. We can do it factor by factor, so we end up with just the determinant of d because the v and v inverse determinants cancel out. And since d is a diagonal matrix, the determinant is just the product of the determinant. Finally, let me mention without any proof that using this v D and P and A matrices defined before. And now using yet another notation for the roots of unity. Sometimes the omega is used as the first of these nth root. That means e to the 2 pi I over n. Then we can define this Fn matrix as 1 over square root of n times V, which is 1 over square root of n, and substituting V, in V the omegas. So this is the first root in the nth root, and the other roots are just different powers of that. So here we get the first root, then the second root, and the n minus first root. So this is actually called the Fourier matrix, which is called also discrete Fourier matrix, used extensively in engineering and numerical analysis. Extremely important matrix. It has the property that if you multiply Fn with the Hermitian from the left, then is the identity. So that means that the inverse of the F matrix is just the Hermitian transpose. And we also have that P equals to the Fn times D times Fn Hermitian. And we also have that A equals to Fn times the polynomial ability that the D matrix times Fn Hermitian. And so the proof of this is kind of technical. It becomes more and more technical, and all this relies on the previous one. So it's kind of tedious to remember all these properties. But I wanted to emphasize that all these special matrices have actually important applications in engineering and sciences.